Now let's see exactly what a heap is. We will look at its shape first, and then at its ordering rule. A binary heap is a complete binary tree. Every level is full except possibly the last one. The last level fills strictly left to right, with no gaps. That completeness is what lets the tree live in a plain array, with no pointers at all. This tree holds 6 values. 16 sits at the top, then 14 and 10, then 8, 7, and 9 on the bottom. The same 6 values sit in this array, in the same order. Read the tree left to right, and top to bottom, which we call level order. Read that way, the tree is the array. Here is why that packing works. The last level has no gap on the left, so every node's array position is predictable. The index arithmetic on the next slide uses exactly that. Now a warning. You may think any binary tree packs neatly into an array. It does not. Only a complete tree, with no gaps, keeps the indices dense and the parent and child formulas exact. A tree with a hole in it would need a placeholder in the array for every missing node, and the formulas would stop matching. Completeness is about shape. A second, separate rule is about order. This is the max-heap property. Every node's value is greater than or equal to both of its children, so the maximum is always the root, but a heap is not fully sorted. Siblings and cousins have no required order between them. Check it on the tree from before. 16 is greater than or equal to 14 and 10 at the root. 14 is greater than or equal to 8 and 7. 10 is greater than or equal to 9. Every parent beats its children. That is all a heap promises. You may think a heap is mostly sorted. It is not. Only the root is guaranteed to be the maximum. At index 1 and A at index 2 have no required order, and the smallest value can sit anywhere at the bottom. A heap promises just one thing. Every parent is at least as big as its own children. Because the tree is complete, a node's position in the array tells you its parent and its children. You need no left or right pointers at all. The formulas are short. The left child of index I is at 2i plus 1. The right child is at 2i plus 2, and the parent of index I is at I minus 1 over 2. This is integer division, and the indices are never negative. These are the zero-indexed forms to match our zero-based arrays. The textbook one-indexed forms look a little different, but the idea is the same. Let's predict first. There are no pointers on screen, so work it out from the formulas. Part A, the parent of index 9 sits at which index? Part B, the two children of index 4 are at which indices? Pause here. Here is the answer. The parent of 9 is 9 minus 1 over 2, which is 4. And the children of 4 are 2 times 4 plus 1, which is 9, and 2 times 4 plus 2, which is 10. So index 9 is exactly index 4's left child. The two formulas invert each other. Whether 9 and 10 hold live values depends on the heap's current size.